So electrolysis is where we're doing the opposite of what's happening in a voltaic cell. We are using an external source of energy to cause a non-spontaneous reaction, redox reaction to occur. And so that's called electrolysis. The combination of hydrogen and oxygen to form water is a spontaneous process. That's what's used in the hydrogen fuel cell. If we supply electrical current, we can cause that reaction to occur in reverse. So someday it may be practical that we can use renewable energy sources like solar power or hydroelectric power, some other source that's renewable, and use that to generate the hydrogen fuel from water to run the fuel cells. We don't have that going on yet, but people are working on it. And it seems like a great idea. So here, a battery, you've got water in here, and at the anode, you're going to have oxygen forming, and at the cathode, you're going to have hydrogen forming. Other uses of electrolysis, other than just generating hydrogen for fuel cells, we can get metals, pure metals, that are not found that way in nature. Most metals are found as compounds, ionic compounds, salts. And so how do you get pure sodium? Well, you call up the chemistry supply store and order it, right? Where do they get it from? You can't go out and mine for sodium because sodium is really reactive. It reacts with moisture in the air, and so, it's just not going to be sitting around. You can take molten sodium chloride. Sodium chloride is pretty easy to come by. You can melt this. It will melt at a very high temperature, and then apply a voltage source, and you can cause the sodium ions to be reduced to form sodium metal, and then the chloride would be oxidized to form chlorine gas. You can also use electrolysis to plate metals onto other metals. So this is a pretty common process. They used to make a silver tea service or silverware out of silver, right? Really expensive. What's much cheaper and looks just as nice is silver plating. And so you make the object out of a less expensive metal, and then using electrolysis, you put a layer of silver on the outside. And so you can make an object that looks the same for a lot less. So here, an object, a ring, we're going to plate it with silver. And so we've got actually the same reaction, but opposite, happening at the anode and the cathode. We've got silver, the silver electrode here, being oxidized to form silver ions, and then over here the silver ions are being reduced onto this metal ring that's functioning as the cathode. Any questions?
Is there something related to this in DNA?
In DNA? Well, there are a lot.
The gel electrolysis?
Oh, yeah. You can use electrolysis. It's called electrophoresis. And so you've got a gel medium. It's kind of like Jell-O, but without the sugar. And by applying a voltage across that, you can cause charged things to move through the gel. And they will move at different speeds depending on their charges and their masses. And so you can use that to separate things, and that's one of the techniques they can use to look at different parts of DNA. Yeah. So how much voltage you need to produce electrolysis depends on the specific half reactions. Here we've got a voltaic cell with zinc and copper. Here we have an electrolytic cell with zinc and copper. And so If we let this one go, it will produce copper on this electrode, and it will dissolve the zinc from this electrode. If we apply a voltage source that causes the voltage to go in the other direction, we can make the opposite reactions occur. So when we do that, we're switching the identity of the cathode and the anode, right? So in an electrolytic cell and a voltaic cell, the anodes and the cathodes are going to be reversed. But what's always true is that oxidation occurs at the anode, reduction occurs at the cathode. Question?
So then if a metal ion gains the electrons to make it into a charge, it'll turn into a solid?
Yes.
Like the general rule of thumb?
Yeah. So if you have a zinc ion being reduced, gaining electrons, forms zinc metal. Zinc metal is a solid at room temperature, and it's not soluble in water.
Is there like any big exceptions to that?
I can't think of any exceptions.
Cool.
This case over, this case where you have a molten ionic compound is a little bit different, but you're still going to be producing probably solid sodium. This is at a very elevated temperature, so it would kind of depend on the melting point of the metal. So in summary, always in all electrochemical cell, oxidation at the anode, reduction at the cathode. In a voltaic cell, the anode is the source of the electrons, and the cathode draws the electrons. So the anode is negative and the cathode is positive. In an electrolytic cell, we're pulling electrons away from the anode, so the anode is positive. It's the positive terminal of the energy source is connected to that to pull electrons away from it, and electrons are being forced into the cathode, and so the cathode is connected to the negative end of the battery, or the voltage source.
It's still anode to cathode, it's just charges are switched?
Right. And that's why, when you go to jumpstart a battery in your car, you don't want to switch the leads. You don't want to mess them up, because then you're going to cause the reaction to go in the opposite direction and very quickly, and then you could have an exploding battery. Or like my son and his friends, you can burn out the starter in your car. Yeah. If the battery cables or other components in the car start smoking, yeah, you should stop right away and don't do that again. Lesson learned. Only costs about $500. So how do we predict what the products are going to be? Well, if we're doing molten salts, it's pretty easy because you only have two things in there. So molten sodium chloride, you've got sodium ions, you've got chloride ions. Those are the only things there. They're the only things that can react. Chloride ion is already reduced. It can't be reduced any farther, so that's going to get oxidized. Sodium cannot be further oxidized, so that's going to be reduced. And come on, pointer, shape up. What's a little unusual about these equations here is we're used to seeing chloride aqueous. Here it's chloride liquid, okay? And that's because this is happening at a very high temperature, and there is no water present here. It's just pure sodium chloride. Why do we do this in molten sodium chloride and not solid? Does a solid ionic compound conduct electricity? No, because the ions aren't free to move. When you melt it, put it into the liquid state, now the sodium and chloride ions are free to move, and so then you can have electric current flowing through it. If your molten salt has more than one cation, then you have to look at which one of those is going to be reduced. It's whichever one is easier to reduce. And so then you go look in the list of reduction potentials. It's important to remember that those standard potentials do not apply to molten salts. Those are for aqueous solutions at standard conditions of 1 molar concentrations. So the values don't apply, but the order is the same. So if we look at sodium ion and potassium ion in the table, we see that the standard reduction potentials are negative 2.71 and negative 2.92 volts. So these voltages don't mean anything, but the relationship of them tells us that the sodium is the one that will be reduced and the potassium will not. So when we're looking at these, a positive electrode potential is one that's going to occur more easily than a negative or a large negative one. This is a very large negative potential, and so that's why you have to apply a significant amount of voltage to reduce the sodium ions. Similarly, if there's more than one anion, like you've got sodium bromide and sodium chloride mixed, you're going to look at the electrode potentials for those two ions. Okay, so we need to read this small print here. So in your textbook, regardless of whether they write the half reaction as an oxidation or a reduction, they list the standard potential from the table, which is for the reduction reaction. Okay? And I think we've all agreed that that can be a bit confusing. So my way is, if you're going to write this as an oxidation, the number's the same, change the sign. So if I'm looking at these reactions of bromide and chloride being oxidized, I'm going to write the half reactions as oxidations. I'm going to change the signs on these. And then I'll look at these and say, well, which one is going to happen easier? It's the one that's more positive, right? So bromide will be oxidized and the chloride will not. Any questions about that?
Wait, so the one that's more positive?
More positive.
If you switch the signs of both of those, isn't the chloride more positive?
No, if we change the signs, yeah, if we change the signs, then the chloride's more positive. This is my way, because this is my slide. So I switched the signs already.
Oh.
So these are correct for these half reactions. Yeah, I'm sorry, it is confusing.
I thought those were the quick values that
No,
switching.
no.
You already switched them.
I already switched them, yep.
It's the same, it's split.
Yeah. So this is an oxidation, and so I'm writing the potential for the oxidation. The book doesn't do that. Don't know why. I'll not go into that. Okay, so in an aqueous solution, this is a lot more common. Predicting products in aqueous solutions is a little trickier because you can get electrolysis of the water itself, right? So let's look at the half reactions for the electrolysis of water. So the oxidation is water losing electrons to form oxygen and hydrogen ions. The standard potential here is minus 1.23 volts. But pure water is not a standard condition. Standard condition would have to have 1 molar hydrogen ion. So that would be a fairly concentrated acid solution. So what is the concentration of hydrogen ion in pure water? 10 to the minus 7, right? So this is 10 to the minus 7, and so we can use the Nernst equation, and E cell equals the standard potential minus 0.0592 volts over N times the log of Q. Here's our standard potential. Calculating Q, we'll put in 10 to the minus 7 for the hydrogen ion. We'll put in 1 for the oxygen, because we can do that at 1 atmosphere without an issue. We don't have to do concentration for water because it's liquid. So it's going to be that 10 to the minus 7 to the 4th power times 1, and that's going to be Q. So it's actually 10 to the minus 28. So you do that, and you end up with the actual potential being minus 0.82 volts instead of minus 1.23 volts. The reduction is water being reduced to hydrogen gas and hydroxide ions. Standard potential is minus 0.83. You do the similar calculation, and you find out that in pure water, it's minus 0.41 volts. And I am using my understanding and writing these with the correct sign for the reaction, so that to look at the overall potential for this cell, we just have to add those two together instead of figuring out which one to subtract from the other. So the cell potential here is minus 1.23 volts. So 1.23 volts, that's not so high. A 9-volt battery has 9 volts, right? So, actually, I'm going to get one and we're going to see. So I just took a big beaker of DI water and I dropped a brand new 9-volt battery in it. And we're watching it and nothing's happening. We should be able to do electrolysis on water, right? Because it should take 1.23 volts to run. Why isn't it going? It's on the slide.
Oh, yeah.
It's not conductive. So there's this voltage across these terminals, but there's nothing that's conducting that's going across. So I should. So what's going to happen? I should have like salt, but I've got baking soda. So you see, I sprinkled some baking soda in there. And now do you see the bubbles coming up from those terminals? The baking soda, or any soluble ionic compound, is going to turn that water into a conductive solution so that the ions can move across from one electrode to the other and carry the current. And then we get oxygen gas forming at one and hydrogen gas forming at the other. I thought I had a picture, but I guess I don't. Well, it's basically this picture way back here. Wait, come on. That one. You can actually rig that up with test tubes and collect the gases. That could be fun. You could, combine them afterwards and make a boom. Now I'm lost. Okay, that's where we were? Okay. So what if we have a sodium iodide solution? So we've got sodium ions, we've got iodide ions, but then we also have the potential to have the water itself being oxidized or reduced. So we look at the two possible oxidation reactions, water being oxidized and iodide being oxidized. So because of the concentration of hydrogen ions in water, this is not an acidic solution. This is the potential for the oxidation of water, minus 0.82. And iodide ions, the oxidation potential is minus 0.54. So which is more positive? More positive is the same as less negative. Yeah, minus 0.54. So this one is going to happen first. And then we look at the reductions, and we've got water being reduced, that's negative 0.41. We've got sodium ion being reduced, that's negative 2.71. Well, that's a no-brainer. It's going to be the water. So at each of the electrodes, whichever half reaction occurs easier, is more positive or less negative, is the one that will actually occur. So you cannot get sodium metal from sodium ions in an aqueous solution because you reduce the water instead. So you can only do that in a molten solution. Well, it's not a solution, a molten salt. Any questions about that? So here's an illustration of electrolysis of an aqueous salt solution. So we've got iodide being oxidized at the anode, and we have water being reduced at the cathode. And the sodium just hangs out. Just to make things a little more interesting, there's something called overvoltage. And this gets kind of complicated, so you don't have to understand what it is or how to calculate it. You just need to know that it exists. An overvoltage is an additional voltage that has to be applied to get some non-spontaneous reactions to occur. So we've been looking at this oxidation reaction for water producing oxygen and 2 electrons, and we can calculate that the potential is minus 0.82 volts. But because of kinetic factors that are too complicated to discuss in Chem 1B, the actual voltage required is about 1.4 volts, not 0.82 volts. And it's due to that overvoltage. Okay, so predict the half reactions occurring in the anode and the cathode for the electrolysis of aqueous sodium sulfate. So we have to consider the possibility of water being oxidized and or water being reduced. So we've got, let's list our 2 oxidation reactions and our 2 reduction reactions. So we'll look at water. And water being reduced, adding 2 electrons, and we're getting oxygen and hydroxide. I can't remember the potentials. No, we're getting hydrogen ions. Nope, that's the other one, never mind. These are the guys we need. So reduction, we're getting hydrogen and 4 hydroxides, and that's minus 0.41. Let's see if I can remember that. And then for the oxidation, that one was minus 0.82 volts. And there we've got water going to oxygen plus 4 hydrogens. And I don't know what I'm doing here. And 2 electrons. Did I get that down correctly? So what could happen with the sodium and the sulfate? What could the sodium do? Sodium ion, would that be oxidized or reduced? Yeah, so Na plus, is that going to lose more electrons? No, it's going to gain. Reduction is gain. So that's a possible reduction reaction. Aqueous sodium ions plus an electron to form sodium metal. So that one is right here, minus 2.71 volts. So which of those is going to occur? The water. So water's going to be reduced. So that's the winner for the reduction. Even with any overpotential, that's definitely easier than minus 2.71. What could happen with sulfate? Any question?
That was because it was less negative.
Yes, less negative. Less negative is the same as more positive. Just sounds weird.
Are you talking about the ions for the sodium sulfate?
Yeah, so you've got two ions, right? You've got sodium ions and sulfate ions. And so those are the two things that could do something, be oxidized or reduced, besides the water itself.
So are you basing it off the energy potential, or off the fact that like the ions, the anions can only give electrons, and the cations can only receive?
There are exceptions, but in these examples, sodium only forms one ion. In order to pull a second electron off of it, to oxidize sodium ion to sodium 2+, requires a lot of energy. It's not going to happen.
So then would an instance be like something on like the fourth row of the periodic table?
Well, you could have transition metals that form more than one ion, like lead can be +2 or +4. So if you had Pb2+, that could get oxidized or it could get reduced. Then you'd have to look at the potentials, yeah, and see which is more likely to occur. All of these are negative, meaning this isn't a spontaneous reaction, but we want to know when we apply voltage to this, what's going to happen. So sulfate, I looked through the table in the back, that list of electrode potentials, and there's not really any great reactions with sulfate. The only one I saw involved it going to sulfurous acid, but that involved acid, hydrogen ions. And we don't have hydrogen ions here, not substantially, right? If this reaction occurs, we'll have hydrogen ions, but this is forming hydroxide ions, and this is just an aqueous solution of sodium sulfate. It's not an acidic solution of sodium sulfate. So there's really nothing we can find in the table for sulfate. Now, if you've had chloride or iodide or sulfide or something, you might be able to find that in the table and compare the cell potentials. So in this one, oops, we're also going to have water. So here, the water's going to get oxidized and the water's going to get reduced.
So what does that mean for the sodium sulfate?
It means the sodium sulfate is spectators.
They're just chilling.
Yeah, they're just chilling. Just like the sodium and the hydrogen carbonate in our beaker here. They're not being oxidized or reduced. They're just conducting current for us. Any questions?